Good evening. Welcome to the RSES Technical Webinar Series. I'm Sean Lundeen, RSES Senior Customer Service Representative. I would like to welcome everyone to tonight's webinar titled Calculating Combustion Air for Fuel Burning Appliances, presented by Bryn C. Cooksey, Senior, CMS RCT. If you don't know Bryn, he has been in the HVACR industry for over 20 years. Bryn specializes in industrial HVAC, maintenance, service, equipment performance testing, and building science. A genuine product of his environment, he started his career as an employee of his family's heating, cooling, and refrigeration business. He is currently the owner and general manager of Air Doctors Heating and Cooling in Belleville, Michigan. Bryn is an RSES certified technical trainer and a certified technical educator from the ESCO group. In addition, Bryn is also an associate professor with Washtenaw Community College in Ann Arbor, Michigan. Bryn is also a training consultant for mechanical contractors, HVACR supply distributors, and HVACR training organizations. Bryn is a regular technical contributor for the RSES Journal and RSES Webinar Series. Bryn holds several degrees and certifications in the HVACR and building science industries. Bryn also holds 5 RSES Certificate Member Specialist certifications, 1 in electrical, commercial, air conditioning, dynamic compression, domestic specialist, and heating. Bryn has also obtained all of the North American Technical Excellence Service and Installation certifications. Bryn is an active member of many trade organizations, including ACA, ASHRAE, and RSES. Tonight's presentation will last approximately 45 minutes, and afterward there will be a Q&A session. Please submit any questions that you'll have throughout the presentation using the GoToWebinar dialog box on the right-hand side of your screen. We'll be fielding those questions tonight to our speaker, so give them some good ones. This presentation is being recorded and will be available for online viewing at your convenience as soon as possible. Now I'd like to introduce our presenter, Bryn C. Cooksey, Senior, CMS RCT.
Thank you, Sean. All right, well, good evening, everybody. Thank you for attending tonight's webinar. All right, today we're going to be talking about calculating combustion air for fuel burning appliances. All right, so here's our learning objectives. We're going to describe the combustion process and why do we need combustion air. We're also going to talk about what happens if we install equipment improperly without considering combustion air. And then we're going to talk about 2 methods to calculate combustion air, and those are the air infiltration method, and then we're going to talk about how do we mechanically supply combustion air. All right. This presentation is based largely in part by the International Fuel Gas Code. It's a code reference and standard that is adopted in many states in the U.S. and Canada. It's co-sponsored with the National Fire Protection Association's NFPA 54, which is the same book, it's just co-sponsored. So the bulk of our calculations are based on those code references. Also, some takeaways from this are actually in manufacturer's installation instructions. And we have to put out the blanket statement that you always want to consult your local authority having jurisdiction. They may have stricter requirements for your particular neck of the woods. All right, if you're looking for more information, we did write an RCS article back in February 2019 with the same title, and I believe that you have access to that as an archive. All right, as we get going, we need to talk about our application. So when we're talking about combustion air, what scenario or what equipment will we be applying it to? For starters, we'll talk about the different categories. So for category 1, we're looking at something that's going to have an efficiency 83% or below. It's not going to condense, and I'm going to have a negative flue pressure. All right, so generally these pieces of equipment are induced draft furnace and boilers or natural draft, and they can be standalone or they can be commonly vented. Additionally, when we talk about combustion air, we talk about category 3 appliances. So these are larger industrial boilers, typically 83% or below. They have a non-condensing exhaust flue piping. All right, but the flue is actually pressurized. This will be primarily large industrial boilers you may see in a hospital or a large facility. All right, so that's category 3. And then category 4, and you may be thinking, well, wait, category 4 shouldn't apply to this. It can. Category 4 is above 87%. It's condensing and the flue pipe is pressurized. However, it only becomes a consideration if the installing contractor was to use a single pipe, where they'll get combustion air from the space and just use another pipe for the exhaust gases. This arrangement is not recommended because if you do, you have to account for combustion air, which we'll talk about here in a minute. All right, so let's do a quick review. All right, what do we need for combustion? We need air, we need fuel, and we need a source of ignition. Put those together, we get a fire. All right. Now, when we're talking about air, we're actually specifically looking at the oxygen content that is inside the air. So roughly around 21% of the air in the atmosphere is oxygen. So when we say air, we really mean oxygen. We can't get the oxygen to the burner without air. All right, so when we say air, we're actually referring to the oxygen for combustion. All right, so when we're talking about setting up appliances for proper combustion, we're basically saying we have to ensure that they have enough air for combustion. All right, now what that air does, it mixes with a fuel and creates a combustible mixture as my fuel comes in. CH4 is the chemical compound or nomenclature for natural gas. As my primary air comes in, the air and fuel is going to mix and then it's going to combust. All right, so I have primary air and I have secondary and excess air. When we talk about supplying combustion air, what we're referring to is supplying enough air to support good, clean, complete combustion. Okay. So here's a definition of the International Fuel Gas Code. When we talk about combustion air, it's air that is necessary for complete combustion of a fuel, including theoretical and excess air. So that air we use to support combustion with primary air, and then also to support complete combustion with secondary excess air. Right. Now, I'm going to be referring to a term, and I kind of want to get it established as we move on in our presentation. That term is called a combustion appliance zone. And what we're going to be using that, we're going to be describing a space. Where do my appliances actually live? All right, it's a physical location. Other people may refer to it as a furnace room or mechanical room, but we're going to call it a combustion appliance zone. When we install equipment, we need to have the design goal in mind that we want to get complete combustion. In order to do that, we have to ensure that that appliance, whichever application range we're dealing with, either has enough space, enough volume for complete combustion, or we're going to supply it through a mechanical means. All right. Complete combustion is also going to help us keep that equipment running at peak operating condition and also help us to prevent carbon monoxide generation. All right. So what happens if you don't have enough combustion air? First things first, you get incomplete combustion, which can cause carbon monoxide generation. And we know carbon monoxide is bad, but it is also extremely wasteful. Carbon monoxide still has heating value in it. And when you purchase units of gas from your utility supplier, you purchase those units of gas or fuel. And if you don't get the energy out of it, you still paid for it and you didn't get your money's worth. So when we don't burn our fuel completely, we leave a little money on the table, if you will. All right. We can get soot formation, which acts as an insulator, which is also wasteful. It can damage our equipment. And then there's other harmful byproducts, which includes toxic alcohols, ketones, aldehydes, NOx, and other harmful byproducts. Some of these are pollutants, and some of them are indoor air quality problems that can affect humans. All right, so not burning our gases completely has some other side effects outside of it being carbon monoxide and wasteful. All right. Showing you that carbon monoxide is wasteful, right here what we're looking at are the limits of flammability. If you look at the explosive range, this goes to show you that carbon monoxide has heating value in it, and I can actually get it to combust. Right. So again, I paid for that fuel from that utility supplier, but I did not get my money's worth. All right. Now we're going to look at scenarios, how proper air being supplied, how it's going to support clean combustion. So in a perfect world, which we're not in, or we don't have in our business, all right, I have CH4, which is the chemical nomenclature for natural gas, and then I have oxygen, roughly 2 parts, and nitrogen. All right, when I put these into a combustion process, I get a flame, and then I get my products of combustion. All right, so in a perfect world, I get carbon dioxide, harmless carbon dioxide, harmless water vapor, and as you see, the nitrogen didn't participate. All right, so that's perfect combustion. In this process, there's no waste. All the proper chemical elements mixed appropriately. I have no waste. Carbon dioxide, water vapor, and nitrogen didn't participate. Here's what we're striving for in our business is complete combustion. So we can't control our burners perfectly in a dynamic environment, whether a home or a business. So we always have to supply excess air. All right, so that excess air is combustion air that we're giving to ensure that that appliance have enough air for combustion. So I still have my chemical molecule, I still have my air sample, but I have a little bit additional just for some insurance. I put those into the combustion process. All right, the fuel burns. These are my products of combustion. So I still have carbon dioxide. I have H2O, water vapor. And as you see, my nitrogen didn't participate, and then not all of my excess air participated. All right, it was insurance. We supply combustion air to get complete combustion. All right, here's what'll happen if you don't have complete combustion or if I don't supply combustion air. I got my same fuel molecule, and I got half my air sample. Right? Put those into my combustion process and look at the results. I have water vapor, unburned hydrogen, and carbon monoxide, and the nitrogen still didn't participate. Right? This unburned hydrogen and carbon monoxide still has heating value. Not only is carbon monoxide bad from the standpoint of it being a poisonous gas, it's wasteful, and unburned hydrogen also. Okay? So that's the first thing that can happen, that appliance starts to burn badly. All right, start to get poor combustion. Also, I can also not supply enough combustion air, and I can affect the pressures that appliance needs to have a positive draft going up the chimney. All right, so we're going to introduce a new term called spillage. All right, so spillage is exhaust gases coming back. All right, they're trying to go up the vent system. They can't, either a chimney problem or in this case, combustion air, lack of. All right, they come back. Now, this sets up an extremely dangerous situation where we just indicated that the exhaust gases are possibly have high content of carbon monoxide. Now I'm going to give them a path back into the building. All right, so combustion air is an absolute necessity. And as we just highlighted, carbon monoxide is colorless, odorless, and tasteless. In an extreme case of spillage or backdrafting, I can actually physically get the flames inside that piece of equipment to come out. We call it conditioned flame rollout. All right. Serious fire hazard can be caused by blocked chimney, depressurized combustion zone, or lack of combustion air. All right. So we have other consequences outside of just bad combustion. And that brings us to our first poll question. Sean?
All right, so the first poll question, what is combustion air? A, makeup air. B, air is necessary for the complete combustion of a fuel, including theoretical air and excess air. C, ventilation air. Or D, a byproduct of complete combustion. All right. Looks like everyone's. All right, I'm going to close the poll in a few seconds here, and I'll read the results. All right. So the poll question was, what is combustion air? The answer was B, air is necessary for the complete combustion of a fuel, including theoretical air and excess air. Pretty much majority chose B or B2. 8% chose answer A, which was makeup air, and 5% chose C, which was ventilation air, and 0% chose option D. And now back to you, Brett.
All right, thank you, Sean. All right, we'll discuss why those are often confused, makeup and ventilation air. All right, so next, full compliance. So when we talk about combustion air, um, it's really not an option. It's really a code compliant thing that you must ensure that it's done on every piece of equipment. All right, so you must account for it. And any combustion appliance, whether fuel oil, propane, whatever appliance you're using, if it burns, you have to provide combustion air. So what happens is it's often overlooked by the contractor. Maybe they didn't have adequate training and they didn't commission the appliance properly. Sometimes it's the customer. One example I think of is maybe a homeowner remodels a basement or a mechanical room and they inadvertently seal off that room and they cut off the source of combustion air. So it can be overlooked by both the contractor and the homeowner. Right. When you have a combustion appliance that hasn't been set up properly and let's say it sets up and you have an issue, that can void the manufacturer's warranty. Most manufacturers have kind of specific guidelines they like to see for combustion. All right, so remember this is coming from the International Fuel Gas Code. So the methods are prescriptive, meaning that there's solutions that we can use to implement to get combustion air. For the sake of time, we're going to focus on a couple. One is indoor combustion air, and then the other is going to be outdoor. And remember, these are both coming from the International Fuel Gas Code. All right. Benefits of proper design. When I have adequate combustion air, I can ventilate and cool the combustion appliance zone, and I'm going to maintain a proper draft inside my stacks or chimneys. All right. And then having proper combustion is going to mitigate that carbon monoxide generation. Now, reason why we're bringing this up even more so now is that there's an industry trend where new homes are being built really, really tight from an air infiltration point of view. And what we mean by air filtration, they're being built where the house can't breathe. Many of us have heard that term before. All right. Or there's a trend for weatherization to occur. And weatherization is basically taking an older house and making it tighter so that we can reduce the utility bills. In either case, we have to identify the need for combustion air. Now, ventilation is often confused with combustion air. All right, when we talk about ventilation, ventilation is specifically for diluting harmful products inside your house. Maybe your cleaning equipment, your cleaning chemicals, or an unvented oven or range. You're trying to reduce the concentration of things that are inside that home or building. So ventilation is more so for people. All right, it's more for respiratory health. All right. Some people also call it makeup air, but makeup air can also be used to relieve pressures, but that is not combustion air. Combustion air is a separate term for air specifically for appliances, and it shouldn't be confused with ventilation and makeup air. All right, like we talked about before, it's often overlooked, but it is a separate design consideration. All right, so as an installing contractor or technician, you have to know how much air to supply and how to supply the proper amounts of combustion air, and we're going to talk about that. All right, in the International Fuel Gas Code, there are 5 different prescriptive ways for you to achieve appropriate amounts of combustion air. However, we're just going to cover 2, some of the 2 most commonly used ones. And with that, that brings us to poll question 2, Sean.
All right. Just launch it. So the second poll question is, what is combustion air often confused with? A, CFM natural, B, CFM 50, C, ventilation, or D, dilution air? All right, I'm going to close the poll here in a few seconds. And looks like majority of people got this one right too. The second poll question was, what is combustion air often confused with? Option A was CFM natural, which 5% chose. Option B was CFM 50, which 0% chose. Option C, which was a correct answer, ventilation, 93% chose. And option D, dilution air, 3% chose. Now back to you, Brad.
Thanks, Sean. All right, so now let's go through some calculations. So just to recap, we talked about the combustion process, why the air is important. We just discovered that it's really not an option, it's kind of required, and we have to think about it. Now let's actually crunch the numbers. Our first way we're going to look at it is with indoor supply air method. All right. So when I talk about combustion air coming from the inside, all right, we have to determine a few things. So number one, does that space qualify? Can I use that home? Is that home loose relatively enough for me to use air inside the building for combustion? There's some rules to that. We'll talk about that shortly. Number 2 is where the appliance is located. 3 will be the style or technology of that appliance. And then we also have to look at how many appliances are in that space. Okay? So when we go with the indoor supply air method, we're utilizing the volume of the CAS or combustion appliance zone. We're using where that pieces of equipment physically live at. We're using that volume of space where they live. We're using the air for that space for combustion. One of the advantages is it's cost effective and easy to apply. However, the disadvantage is that I'm relying on natural infiltration air to supply my combustion zone. All right. Infiltration air is air that is traveling uncontrolled into a structure from the outside. All right. So I don't have any control over that. I'm relying on that building being leaky enough to supply combustion air. Right? And we just discussed that buildings are being either made tighter or we're weatherizing homes and buildings. All right, so with that being said, we have to determine how much of that building shell is leaking in order to see if it qualifies to be used in the space. All right, for indoor combustion to be practical, all right, we must have a minimum of 0.4 air changes per hour. 0.4 air changes per hour. All right. So 1 air change per hour is when I turn over every cubic foot of air inside that home or building 1 complete time in an hour. So 0.4 changes, basically 40% of that 1, I have to turn over of airflow from outside to in that building for it to be deemed leaky enough for me to implement the indoor supply air method for combustion air. All right, so to rely on this method, it must always be a constant turnover of infiltration air for the building appliance for it to always utilize it. All right, so first question, does this building qualify? Is it leaky enough? All right. Two ways you can go about and look at that. All right, so you got to test the building. The test methods, you can either go with a blower door test, which we'll describe, or engineering charts. Either one of these methods will give you basically the background if the building is leaky enough. All right. And then once we determine that and we do our job, we always have to do some homeowner training to ensure that they didn't inadvertently put our equipment into a confined space. And we'll discuss that shortly also. All right, this comes from the International Fuel Gas Code commentary. And what this does, this actually shows you that each of the building materials used in our houses or buildings have a air leakage measurement with them. So we can look at all the building components in our building and determine what the air leakage is. It is possible, it is available for use. However, I find it to be tedious. So what a lot of people elect to do is use a blower door test. All right. So what a blower door is, it's a sealed shroud containing a fan. And basically we put that on an exterior opening, typically a door for a building. And that fan, depending on how that blower door is set up, can either pressurize or depressurize my space. And what we're trying to do in this situation is to simulate a 15 to 20 mile per hour wind approaching all sides of the structure at once. All right. With this tool, this blower door, I can quantify my air leakage, and we'll use it to verify the tightness of the structure. If you get into building science mode, I can run a blower door using a thermal imaging camera, and I can actually find the leaks inside of a structure, which could be helpful. When we run a blower door test, there is a test reference number. It's called CFM50, and this is the airflow, all right, cubic feet per minute that the building is leaking at 50 pascals or at the pressure difference that is influenced by the fan. So we use CFM50 in building science basically to make this test repeatable every single time. So CFM50 is a reference test pressure. All right. So we got to do some math. We'll do that shortly. A dwelling or building must have a minimum of 0.4 air changes per hour. All right. And that's a natural measurement. The blower door provides us with CFM50. All right, the fan created a 50 pascal pressure difference. So we got two different readings that we have to handle. All right, so we have to derive the natural airflow from the exaggerated airflow caused by the blower door. All right, how we do that is with these formulas. All right, the first formula, ACH50, is air changes per hour at 50 pascals. All right, so how this formula works and what we're looking for, when I have CFM50 given to me by a blower door, all right, cubic feet per minute, I have to make that calculation become an hour. So I multiply that by 60 minutes. And then in order to get the air changes of that structure, I have to divide that total by the building volume. All right. So I can get a CFM50 number for my blower door, and then I can get HCH50 if I do the math. Right. Once I get HACH50, I simply divide that by 20, and that gives me ACH natural. And that's the number we're looking for. And then remember, when we talk about volume, that's the length times the width times the height of a room in cubic feet. So when we talk about the indoor supplied air procedure, all right, first thing we have to do is verify that that structure did qualify. It was leaky enough in order for us to use this method. All right. If it is not leaky enough, then guess what? I can't use this method for combustion air. I have to use something else. All right. So minimum, it has to be 0.4 air changes per hour. All right. So if it is appropriate, if it is leaky enough, then I simply start by collecting the BTU input ratings on all my pieces of equipment that live in that combustion zone, that combustion appliance zone. Right? And that could be water heaters, dryers, gas fireplaces, ovens, ranges, whatever, furnace, boiler, excuse me, whatever is in that appliance zone, combustion appliance zone, we record the input data plates because we have to supply combustion there for that appliance zone, like so. All right, here I have a water heater in the furnace and the combustion appliance zone, and let's say this 90% furnace was single piped. The installer just stubbed it up above the picture. All right, these two appliances have to be accounted for, so I will add the BTU total up. And then once I add my BTU total up, I will go into my next step. All right, so my next step, once I get my total, I have to understand what a confined space is. All right, it's another definition we're going to throw in. A confined space, the volume of the space must equal 50 cubic feet per 1,000 BTUs per hour. And once again, volume is length times width times height. All right, so here's how you proceed. If the volume of the space is sufficient and an infiltration is acceptable, then you can use the indoor air supply method. Right? If the infiltration is acceptable, right, you are leaky enough, but the volume is not met, then I have to possibly communicate that combustion appliance zone with another area and add their volumes together, like so. All right. So let's work through a problem here. So in this picture, I got a furnace at 100,000 BTUs per hour. I got a water heater at 40,000 BTUs per hour. So my total for both appliances is 140,000 BTUs per hour. Remember, we need 50 cubic feet of air per 1,000 BTUs per hour. Right? So when I do the math, I take 50 cubic feet of air, and I take 140 divided by 1,000 gives me 140. I multiply 50 by 140, that gives me 7,000 cubic feet. All right. So we need a space of roughly 7,000 cubic feet for combustion air for these two appliances. All right. That's roughly a room that's 27 by 27 by 10. Now, I don't know about you, but that's a pretty big room. All right. So some houses may not even have a footprint that large for one room. So we might have to get that from a combination of rooms. All right. Here's how we do it. All right. So let's say this mechanical room is pretty small. All right. And I don't have the 7,000 cubic feet of volume I need to have these appliances operate exclusively in that combustion appliance zone. So what I have to do is I have to connect it to another room utilizing what's called transfer grills. Right? And how it works, I'm taking the volume of the room where the combustion appliances live, and I'm adding the volume of an adjacent room, right? And I'm creating an opening, maybe through the wall surface or door surface, and I'm putting transfer grills to allow the rooms to be connected so that I have a cumulative total of volume that is acceptable for combustion air. Okay? Now, when we go with an adjoining space, all right, we're going to communicate between the two. And notice how we have these arrows here that are going to the equipment and back. All right, we have one high and low because this is going to promote kind of a convective loop that the combustion appliance zone can take advantage of. All right. So when we size our grills, we need to size them at 1 square inch per 1,000 BTUs per hour. Now remember, a grill is not 100% open. You have metal or wood in the way. All right, so we have to know the free area of that particular grill. So once you come up with your calculations, bear in mind we have to add an account for our free area for that louver grill. Okay. When we make our openings, one needs to be 12 inches from the top, one needs to be 12 inches from the bottom, and this is going to promote that convective air current between the two spaces. All right. So let's look at an example. This space right here is 10 by 10 by 8. All right. And this gives me 800 cubic feet. The space adjacent to it is a lot larger. It's 100 by 100 by 8, and this gives me 80,000 cubic feet. So total volume of both spaces is 80,800 cubic feet. Right. And we've already qualified this house. It is above 0.4 air changes per hour, so this space is acceptable. Right. So the equipment we have in space 1 right here, we have 150,000 BTUs per hour with a furnace. We got a water heater at 40,000 BTUs per hour. We have a dryer at 40,000 BTUs per hour, which gives us a combined total of 230 BTUs per hour. All right, remember our rule, we need 50 cubic feet per 1,000 BTUs per hour. So with that 50 cubic feet, all right, we're going to multiply that by the quotient of 230,000 BTUs divided by 1,000 BTUs per hour, all right, which works out to be 230. So 50 times 230 gives us 11,500. So this is the volume that we need for these appliances, all right? So as you see, the room that they were located in, this first room, it wasn't enough volume. However, when we connect it to the second larger room, we well exceeded, and we already qualified the building. We can't use the indoor supply air method for combustion air. And that brings us to poll question 3.
All right, so the third poll question is, what is the minimum ACH natural requirement for the indoor combustion air method? A, 0.10 ACH, B, 0.20 ACH, C, 0.30 ACH, or D, 0.40 ACH? All right, I'm going to close the poll here in a few seconds. And it looks like majority got this one right too. So the question was, what is the minimum ACH natural requirement for the indoor combustion air method? A, 0.10 ACH, no one had answered. B, 0.20 ACH, 5% had answered. C, which is the correct answer, or C, which is not the correct answer, 0.30 ACH, 7% chose, and D, 0.40 ACH, which is the correct answer, 88% chose. And just as a reminder, if you have any questions, don't forget to submit them to the dialog box on the right-hand side of your screen. And now back to you, Brent.
All right, Sean, thank you. All right. So now we're going to talk about our second method for this evening. It's calculating combustion air with mechanically supplied combustion air. When we talk about mechanically supplied combustion air, basically we're bringing in combustion air from outside via a fan. We're bringing air via a fan to supply combustion air to our appliances. Now, typically, we would use this in a few different situations. So, number one, the building did not qualify. It was well below the 0.4 ACH per hour, and the building was not leaky enough. Second, I couldn't get the proper amount of volume. Maybe the appliances were too big for the volume of the space or the adjoining volume, right? Or other methods we didn't discuss. If we try to go outside, the ducts or the openings to supply fresh air, fresh combustion air without a fan to those rooms, they may be too large or impractical. So in this situation, we can deploy a fan to deliver our combustion air, right? So the way we approach this is similar. We need to tally up all the BTU input of the appliances inside that combustion zone, all right? Since we're dealing with the fan and it's what mechanical means, the holes or openings to supply combustion air can be kept to practical limits. And then once we total up our appliances, we take that information and we start to get to work. All right. With mechanically supplied combustion air, all right, we're basically looking for a fan or blower that can deliver 0.3 CFM per hour, 0.3 CFM per 1,000 BTUs per hour, 0.35 CFM per 1,000 BTUs per hour. All right, so that's our number. All right, that's our number, 0.35 CFM. Disadvantage is higher initial costs. I have to purchase a fan, possibly run an electrical circuit. I have to do some ducting, so increased material costs, increased labor costs. Advantages, all right, safe and efficient. You got air supplied directly to the combustion zone, right? So that homeowner can close off that ugly furnace or boiler room, right? What they want to do. Right? When I do this, the vents for the combustion appliances are not affected by building pressure because they have a dedicated combustion air fan. All right. And like I said, it's a better protection against inadvertent remodeling. All right. So after we calculate our appliances, or after we tally them up, right, we get a fan that will be large enough for all the BTU appliances within that space. Right? Now, another provision for the code, if we go the mechanically supplied combustion air fan route, we have to electrically interlock the burner circuit of the appliances with the fan. All right? So on a call for heat, say with the boiler, once that call for heat comes on, I should have some kind of relay or some type of signal to trigger my combustion air fan to start. That is a code provision because you don't want that fan running, dumping combustion air, and it's not needed. Right. So usually with the use of a relay or a pressure switch, pressure switches are preferred. That will prove that you have your combustion appliances operating and that you need your combustion air fan to come on. All right, so on a call for heat, like we just mentioned, the fan should start up. All right, the interlock should shut the equipment down. Once my combustion appliance is satisfied, all right, I should interrupt that combustion air fan and we should be able to shut it down. All right, some energy conservation tips. If possible, you should maybe consider heating the combustion air up prior to it being used for combustion air. It's a couple different ways you can do that. But warmer combustion air has the ability to make combustion happen easier and cleaner, so that promotes fuel efficiency. Right? You don't want to use your combustion fan for any other provisions. So it is not a provision for you to use double duty with any kind of combustion air fan. It is strictly for the combustion appliances. Another thing you want to do is avoid grossly oversizing. Fans come in different ranges where you can comfortably supply combustion air. You don't want to oversize the fans unnecessarily because there is consequences. One, wastefulness if you have too much combustion air. So you just want to supply what's needed. All right. That excess air can also, you have to account for that in your heat loss, heat gain calculations, that combustion air. All right. Again, installation errors, you want to avoid grossly oversizing. All right. You just want to meet the requirements. And if you improperly commission this, you get excessive air, carbon monoxide generation, reduced efficiency, and you can have too much combustion air. Well, it can actually disturb the flame sensing technology with certain boilers. All right. So you don't want to grossly oversize it. All right. So just to recap, you're going to add up the BTUs. All right. It's going to be difficult to interlock a pilot water heater or a dryer or gas fireplace. Those you really can't interlock. However, you still want to account for those inside your BTU calculation. After you tally up your BTUs, you're simply going to use your 3.5 multiplier of CFM per 1,000 BTUs per hour. All right. And once you do that, that is going to help you size that fan. Now, as some maintenance goes, you always want to do some maintenance to check to see periodically that your combustion appliances are operating properly. We're going to talk more about this in the troubleshooting section. All right. All right, so here's an example. I got a 200,000 BTU per hour boiler. I got a 100,000 BTU hour hot water heater. All right, so my total is 300,000 BTUs per hour. When I use a mechanically supplied combustion air method, I'm going to take my 0.35 CFM. I'm going to multiply that by the quotient of 300,000 divided by 1,000 BTUs per hour. That's going to give me 300. I'm going to multiply that 0.35 times that 300. All right, my slide is wrong. It's actually be 105, 105 CFM for this space. Okay. So this particular example would be 0.35 times 300, which would be 105. So these need to be changed. All right. So that brings us to poll question 4.
Fourth poll question: what is an appliance's CFM rate per BTU per hour for mechanically provided combustion air? A, 0.15 CFM per 1,000 BTU per hour. B, 0.25 CFM per 1,000 BTU per hour. C, 0.35 CFM per 1,000 BTU per hour. And D, 0.45 CFM per 1,000 BTU per hour. All right, I'm going to close the poll here in a few seconds. And it kind of looks like everyone pretty much got it right. So the question was, what is an appliance's CFM rate per BTU per hour for mechanically provided combustion air? A, 2% had answered, which is 0.15 CFM per 1,000 BTUs per hour. 7% had answered B, 0.25 CFM per 1,000 BTU per hour. And 88% had chosen option C, which was the correct answer, which is 0.35 CFM per 1,000 BTUs per hour, and 2% had chosen option D, 0.45 CFM per 1,000 BTUs per hour. And now back to you, Bryn.
Thank you, Sean. All right, so let's do some performance verification or some troubleshooting. We're at an appliance is already installed. Maybe we didn't install it, but we need to run some testing to see if combustion air is our issue. Right. So before we do any of our tests, what we need to do is establish worst case depressurization. So a house or building has items in it that act to remove air from that house. Remember, a lot of homes or buildings were built where they're dependent on the shell leakage, the leakage of the actual envelope of the house to supply combustion air. So if that house has the ability to be depressurized, all right, to a great extent, it can actually overcome and not allow combustion air into my combustion appliance zone. It can also cause spillage and backdrafting and flame rollout like we talked about earlier. So to verify that, as a service tech or contractor, you should work to put that house or building in worst case. And worst case means you're going to close all exterior doors and windows. You're going to turn on all the exhaust fans, operate them at maximum speed. This includes kitchen fans, bath fans. All right, turn on the clothes dryer if there's one there. You're going to close the cast door. All right, if it has an attic fan or summer fan, you're not going to operate that. That's typically not going to be on. You're going to close any fireplace dampers. Obviously, you want to make sure the fire is not present in the fireplace. And then when you do this test, you're trying to get the house as negative as possible, but you're not using a blower door. You're using all the appliances in the house during normal operation to make the house go in as negative pressure as possible. Once we get into the worst case or established worst case, that's when we start our training, our testing. All right, so first thing we do, we're going to put our first appliance in operation. And you're going to visually verify that the appliance lights off properly. All right, did I get any kind of flame rollout on startup? Did the flames dance off? Were they really loud? Any kind of visual clues that there may be an issue. All right, if that appliance has a draft hood, you're going to test for spillage. All right, testing for spillage means we're going to discuss it here in depth shortly, but basically you're looking for evidence that the exhaust gases are not going up the equipment. Another test you're going to do is you're going to test for draft, and then we're going to do some combustion testing. So you do that for the first appliance, and then you turn on the subsequent appliance that's inside that combustion appliance zone. All right. Remember, all these tests are going to be done while that building or that home is going to be in worst case. All right. First thing we're going to do is test for spillage. So with spillage is a visual indication. I'm going to use a smoke pen, a fogger, maybe a mirror, and I'm looking for physical evidence that the exhaust gases are coming back. All right, and we're going to make sure that they're not coming back after the 2-minute mark. Where 2 minutes comes from, when I have a cold appliance that's coming on for the first time, after a while, my chimney may be cool. It may take up to 2 minutes to establish a draft. After 2 minutes, if I have spillage, all right, or backdrafting or flame rollout, something like that going on, I have an issue that I need to address. So spillage is going to be a visual indicator that you got a combustion air problem. Once again, it's going to be done in worst case. All right. Testing for spillage. All right. You're going to take that smoke pan, fogger, or mirror. All right. You're going to put it near the draft diverter of the appliance. All right. And you're going to look for that visual evidence to see that the exhaust gases are coming back. Now, after 2 minutes, it is all or nothing. Either those exhaust gases are going up or they're not. All right. Any portion of it, it is a pass-fail criteria. Either it is drafting properly or it's not. Draft is another test that you could take. When I get draft, I'm going to take a manometer, and I'm gonna actually, with a static pressure probe or a reference tip, I'm gonna check the exhaust piping, and I should have a slightly negative pressure for natural draft appliances. All right. Draft can be affected by the height of the chimney, the temperature difference between indoors and outdoors, the design of the chimney, the materials. Typically, when I have a draft, I want to fall in a range of negative 0.02 to negative 0.04 inches of water column. Some manometers can be transferred over to pascals. Pascals is another reference point that you can use. But the key here is it needs to be slightly negative, slightly negative. Now, in worst case, if it is drafting while it is slightly negative, if I have my worst case conditions, as negative as that home can be or building can be, and I'm still able to draft, chances are you do not have a combustion air problem. All right. When we talk about draft, where you're putting your probe is not critical like combustion testing. I'm not referencing any of the flue sample. I'm simply checking the pressure. So I can make it in a diluted space or undiluted, doesn't matter. All right, I want to check it after 2 minutes, and I insert my manometer. Your draft should consistently get more negative as the appliance is coming on. And remember, in worst case scenario, if I am drafting properly, chances are you have adequate combustion air. All right, here's a draft interference test. While you're checking draft, and you do suspect that you have a combustion air problem, all right, you can start to identify what's causing your manometer not to track in a negative direction. All right, so if the pressure is not adequate, you can start by maybe turning your exhaust fans off. Do I have a draft change? You can start by closing doors or opening doors. Did my draft change? All right, do I have excessive cell leakage? In some cases, it can affect my draft. Do I have duct leakage, like leaky return ducts inside my cast? That can cause a negative effect on my draft. All right, and obviously, do I have inadequate combustion air? All right. So with that draft measurement, at worst case, if you see a reduction in draft, you have an issue. If you don't see a reduction in draft, in worst case, chances are combustion air is good. All right. And then the last test you can perform is combustion analysis. Now, combustion analysis, you're taking an instrument that has sensors inside and you're going to sample those flue gases. All right, you're looking at the stack temperature. You're going to be checking carbon monoxide, carbon dioxide, oxygen, excess air, and efficiency. Right. With a combustion analyzer, you always want to get an undiluted sample. So you want to have a sample taken before any air that can mix with those flue gases and dilute your sample. When you do a combustion analysis test, you always want to do it at steady state or after your equipment warms up. And just a recap, you always want to avoid changes in size. You don't want to take it near elbow, changes in direction, stuff like that. All right. And just remember, always get your reference, always zero your equipment outside. Right. It's just a good habit to get into. All right. So here are some images of where you would want to take your combustion analysis measurements at. On the left picture here, this is probably a furnace with a draft diverter. All right. So the exhaust gases come out and they go up the stack like so. If I take my probe and measure the exhaust gases in the stack, I take them diluted, and that's not what I want. So with a draft, natural drafting appliance, like so, I have to actually stick my probe into the cell of each of these heat exchanger tubes, right? When I take it in like a category 1 non-condensing furnace, 80%er if you will, all right, I want to take my combustion analysis measurement and that piping, exhaust piping going over to my chimney stack. All right. Now, this just to show you, remember my draft measurement can be done diluted or undiluted, and my combustion gases, they have to be taken undiluted. They cannot reference any outside oxygen or you'll get a skewed reading. Okay. Here are parameters. So these are pretty industry basic. A lot of manufacturers will follow these. Now, when we talk about combustion testing, when I am in the worst case, that home is in a worse situation because of depressurization, all right, I still should have oxygen range between my 6 to 9 or whatever appliance I'm dealing with. All right, if I don't have adequate oxygen in that range after I verify the fuel gas pressure, then I need to actually start to look and see if I have a combustion air problem. All right. So what you're going to do is you're going to observe the oxygen or O2 readings on your analyzer. All right. What you're looking for is above 5%. With natural draft appliances, some people say 6. Or you can be with a power burner, you can be above 3%. All right. And what you're looking for when you're testing that appliance with a combustion analyzer, all right, and in a worst case, is my oxygen steady? Is it within my ranges? If so, then chances are I don't have a combustion air issue. If it is below my minimum or my range, then it's likely I could after I verified the fuel pressure. All right. One way to tell if you have a combustion air problem, if I have a poor or low O2 reading with my combustion appliance, if I open the door to that CAS or combustion appliance zone, or if I open a window and my oxygen starts to improve, then guess what? You got a combustion air issue. All right, here's some repairs. If you can, with your customers, always opt for sealed combustion appliances, your high efficiency furnaces. And remember to go 2 pipes. If you single pipe, you're going to have to account for combustion air. All right. We also talked about the 2 different methods that are found in the International Fuel Gas Code. Remember, there are many others. These are just two that are often used the most. All right. And then after the repairs are made for your appliance, let's say you do add combustion air, you need to pre and post test. So I need to pre-test, identify my problem. Once I make my repairs or countermeasures, I need to perform some post test. And with that, we will open it up to some questions.
All right. And so the first question, is there any control to maintain hot or cold combustion air supply as well as a pressure controller if the combustion air is too much?
Generally, when I've seen combustion air be tempered in industrial settings, I've seen a dedicated air handler that actually had either electric resistance heat or hot water coil inside that air handler to temper the combustion air for before it goes into the appliance.
All right, and then I got another question here. How do you safeguard against flame rollout?
You safeguard against flame rollout by supplying enough combustion air. If you have enough combustion air, and if the appliance is healthy, meaning not a cracked heat exchanger, no no blocked chimneys or flues, if your chimney is sized properly, you have supplied enough combustion air, flame rollout is really, really unlikely.
And then I got another question here. What if you were just to take the outside air into the furnace and hot water heater?
That is a method. We didn't cover that, but that is a method. However, reason why it is not as common is because if you have a large mechanical set of appliances, a big boiler, or a combination big boiler, big water heater, maybe like an apartment building, you're talking about a pretty large hole that would be impractical. So in that case, most people will go from a indoor supplied air method to mechanical combustion air, but that is a provision allowed in an international fuel gas code.
Um, and then I got another question here that just came in. If ACH is below 0.40, what about care sizing is listed in code books?
Yep, there is provisions for that. However, once it's below 0.4, you're dealing with an extremely tight home, a very, 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 very tight home. And in our practice, we just made it a point that if it's not qualifiable, we go to mechanically supplied combustion air.
All right, and then I got another one here. Does code require if your mechanically supplied air doesn't work to have your system shut down?
A very good question. Yeah, it is interlocked. So if it does not work properly, if your fan fails, you can't make that pressure switch. Your combustion appliance should not be able to fire. It is interlocked. That is a requirement.
All right, and then I have one that kind of goes with this, I believe. How do you mechanically interlock a standing pilot water heater on mechanical air?
You can't. We kind of mentioned that a little while ago.
Okay.
A standing pilot water heater is a low BTU per hour, so the space may qualify. So you typically cannot. You cannot interlock that. However, a lot of the combustion fans have leakage built into them. So even when they're off, they have a small amount of leakage to supply the water heater, and that does meet the provision of the code.
All right, and then I got a last question here for you. So with a mechanical combustion air supply with too much air being supplied, what do we expect and what's the effect that will be on the burner's flame?
So you will see that show up in a combustion analysis test as very, very high excess air. In some cases, if it's drastically oversized, you can start to get carbon monoxide generation, um, really, really high amounts of carbon monoxide generation with too much supplied air. So a combustion analysis test and with those parameters, if it's oversized, then you have to take steps to limit the amount. You just need to supply what you need and the appliance will take care of itself. If you grossly oversize it, then you'll have problems with your analyzer readings.
All right. Well, thank you, Bryn, for the presentation tonight and for answering all those. And thank you to everyone for attending this webinar. Over right here. For those of you who would like to view this presentation at a later date, you can do so in the next few days in the new members only section of rses.org, which I can show you how to get to right now. So, you go to rses.org, log in as a member, click homepage on the top left, and go over to training and click webinars. And once you are logged in, you could view our archived webinars for free. Also, webinar attendees from tonight's live event will receive a certificate for completing 1 hour of continuing education about 1 day after this event ends. If you have any questions, you can email me at webinars@rses.org. Again, that's webinars@rses.org. Thank you again, everyone, and have a great day. This webinar is now concluded.